Hello guys, back with another video, and today's video is slightly different from my standard, hardware demo videos. This is a e-video, so I'm just going to be writing here and more of a derivation kind of involved video here. So yeah, we'll be talking about another DC-DC converter and a standard non-isolated. So the grounds are common, not isolated one, a non-isolated one, and it's along the same lines of the three standard DC-DC converters which we know, the buck, the boost, and the buck boost. But this is the Cuk converter, as you can see on the screen. It's slightly different in the sense that the three ones which we all know are second order systems because there is one inductor and one capacitor, and whereas this one has four, it's a fourth order system. There are two inductors and two capacitors besides the switch and the MOSFET and of course your load. So yeah, our analysis is slightly going to be more involved because we have to now in order to derive all the current and voltage equations as well as the duty cycle, we have to consider both the inductors and of course the capacitors later, the voltage across and the current through them. So yeah, that's what the video is going to be about. And the Cuk converter is a kind of buck boost converter in the sense that it can, similar to the buck boost, it can both step up and step down your input voltage depending on the duty cycle which you give. And yeah, below 50% it will be operating in buck, and above 50% it will be in boost. And similar to the standard buck boost converter, the output is going to be inverted. So if you say, if you give something like 12 volts in and you give say a duty cycle of 50%, you're going to get minus 6 volts on the output, which is the same voltage on the input, half of that, but opposite polarity. As you can see, it's shown here in this diagram. So yeah, now we can go into the derivation then, now that you know the basics. So I'll just go into OneNote here, and yeah, let's begin the derivation. And one more thing to note here is, if you just look at the circuit, the input side of it looks like a boost converter. If you see the inductor in series with the source and the low side switch, whereas the output has the LC filter, which is the inductor and the capacitor on the output. So that looks more like a buck converter. So you, that is the Cuk converter is sort of like a mishmash between both of them, the input and output, and in between there's a coupling capacitor, as they call it. That is what is going to transfer the energy from the input to the output. And that is what makes this converter good, in the sense that it has continuous current which is drawn on the output. So there are less pulses, and basically it's not pulsed, it's continuous, so the EMI goes down a lot. So yeah, it's a continuous current converter. And we have a diode, yeah, of course, in between towards the ground, the cathode. So yeah, it looks like a boost converter on the input and a buck converter on the output. So that's a nice way of remembering it. So just draw the circuit here once. We have our source, we have our inductor, we have our switch. I'm just drawing a generic switch. It can be a MOSFET, whatever, but just a generic SPST switch, single pole, single throw. Then we have our coupling capacitor, and one second, yeah, and we have our diode. We have our LC filter and the resistive load. So yeah, that's the circuit, and let's just give it notations. This is Vs, our supply voltage. This is V naught, our output voltage, and L1, L2, C1, D, C2, and we can call this Q, which is our switch. So we have the circuit now. So to first of all, the first derivation we can do is the duty cycle one, deriving the duty cycle formula in terms of the input and output voltage. And that's the first step, because you need to know what duty cycle you want to run the converter at. So first of all, we'll derive that, and for that what we can employ is known as the volt second balance for an inductor, which states, it's a fundamental principle which states that the average voltage across an inductor is basically has to be 0 for one switching cycle, because you know that according to the main equation, in the steady state there cannot be any voltage across the inductor. So yeah, average voltage across inductor in steady state is 0. So that is the fundamental principle, what is known as the volt second balance, and that's what we're going to be using to derive the equation. So first what we'll do is we'll write the equivalent circuits of this converter in the on and off state, and let's do that first. In the on state, can do that, and now you can see in the on state is basically when the switch is closed, so it's going to be the supply voltage, we're going to have that, and yeah, this switch is closed now, and the capacitor is here, we have the inductor, the second capacitor, and yeah, the load. So just writing all the R, that's our resistive load, so R, C2, L2, C1, L1, and just to show that the switch is closed, we can see this is closed, and this diode is basically going to be reverse biased, so that is going to be open circuited, so I'm not drawing that here. And in the off state, that is our second, I will write that circuit after this. Let's, or we could do it right now itself. Yeah, we can just do it now. So in the off state, basically the switch is open here, so now the circuit becomes like this. We have the inductor, now the capacitor is in series with it, as well as it is in series with this inductor and capacitor here. But one difference here is these two are not in series. Actually, the diode is going to be forward biased here, because you can see the current is going to be flowing in this direction. So yeah, the diode is going to be forward biased. So assuming it's ideal, assuming ideal switches here, diode as an ideal switch and the actual switch as an ideal switch. Again, this is the closed diode. We have a capacitor, and yeah, we have our output here. So writing all the notations again, it's nice to write these notations so that you don't have any confusions later. So yeah, writing all of that, V naught. So yeah, now we have our two equivalent circuits, and this now we'll derive the equations. So in the on state of the switch, we have to write for VL1. So looking at this, you can see here, it's basically just the voltage, supply voltage. This is one closed loop here. So looking at that, VL1 is basically just Vs, and VL2. Now looking at this, we can write the KVL equation. So the KVL is basically, if we go from this direction, let's assume one direction, that's a thing which we can do in the start itself. Let's assume that the polarity is like this and the current direction is this. Same for this inductor. Let's do this, and one main thing is, once you assume one direction, keep it constant, don't change it, so that you have a constant, and you get the correct, because often, if you flip the outputs, then the answer will, the signs change, and then you might not get the correct answer. So just assume one direction. So I'm assuming left to right, which is standard. So looking at it that way, if we write the KVL equation here, we're going to get VL2 is basically equal to minus VC1 minus VC2. And if I can just write it for you here. If we go in this direction, since we are assuming it's here, it's going to be plus VC2, then going back around here, plus VC1 plus VL2 equal to 0. So yeah, if you just shift it here, you get this equation. Now moving on, we have the two equations for the inductors in the on state. Now for the off state, VL1 is, now again you can write the KVL here. It's basically Vs minus Vc1, and VL2 is equal to, if you just again write the KVL for this loop, now this is the loop, so you write this here, VL2 is basically equal to minus Vc2. And if you get confused about the polarity here, another way you can write this is, just look at the left. Basically VL2 is the voltage difference, across the L2 inductor, right? So if you just looked at the left and the right side, VL2, just look at the left side, it's basically connected to ground. So you can say 0, and always anyway potential difference is something minus something, right? So if you look at it that way, the left side is 0 minus the right side, and assuming that it's plus and minus, you can assume it's same as before. Plus and minus, it's going to be minus VC2. So yeah, you get minus VC2. So that's another way you could do it if you have confusion in the KVL. So now that we have the 4 equations here, these are our equations, and now we can move on to writing the duty cycle equation, and for that now we'll use the volt second balance as I said. So let's write, according to the volt second balance, the average voltage has to be 0, right, for one switching cycle as I said. So we can say that VL1 in the on state into T on, which is the on time, plus VL1 in the off state into T off is equal to 0. So whatever I just said as a statement, I just wrote it mathematically. So now moving on, VL1 in the on state, we can just substitute. That's why we wrote these equations. So substituting from here, Vs into T on, plus in the off state, it is Vs minus Vc1 into T off equal to 0. So if I just draw the graph here, the waveform, it's this same thing. We have the on state and the on state and the off state. So this is your T on and this is your T off. So you can say this is your waveform, and the duty cycle is basically T on by T on plus T off. So we know that, and looking at this equation, moving on, we can just open this bracket here. So Vs plus T on plus Vs T off minus Vc1 T off. So now we have this. Now this is done for the first inductor. Now again we can apply it for the second inductor. Now this was for L1. Now for L2 we can write VL2 non-state similarly as we wrote before. So yeah, now we have this, and yeah, just look at the equations again. Minus Vc1 minus Vc2 to T on plus minus Vc2 into T off equal to 0. So we have this now, and similarly just expand the brackets. So now that we have this, let's just rearrange and get in the final output which we want, which is the transfer function between the output voltage and input voltage and the duty. Those are the only 3 variables which we want. So basically we need to find Vc1 in terms of Vc2 so that we can substitute it in this equation. Let's call it 1. So you can see here we have Vs, but we have Vc1, which is a third variable. We don't want that. We only want Vs and Vc2, and if you can see here, basically Vc2 is the voltage across this capacitor, which is basically our output, right, because it's in parallel with the load. So Vc2 and Vs, that's what we wanted in terms of. So if we just rearrange it here and shift this to the other side, and if we take Vc2 common, it's T on plus T off. So now that we have this, we can say Vc1 is minus Vc2 to this divided by T on. So now that we have this, we can simplify this further. We know here, as I wrote this, D is T on by T on plus T off, and T on plus T off is basically, you can call it TS, which is your switching time, which is the total time. And yeah, if this total thing, because this is one cycle, right? So you can call this as TS. So this is your switching time, and just rearranging this equation, T on will basically be duty times your switching, whereas T off will be 1 minus D times switching. So these are fundamental equations. So yeah, they always help in writing, because if the duty is say 40%, and 40% is in percentage, so if you write it in numbers, it's 0.4. So the remaining off time has to be 1, right? Because 100% of 1 is the maximum duty. So the off time will be 1 minus D times the switching time. So if we just substitute this here, we're going to get minus Vc2 into Ts basically, which is T on plus T off divided by, and yeah, substituting this, T on is D times Ts. So this thing and this thing will get cut. So you get this as minus Vc2 by D. So now that we have this equation, we can go back to this equation number 1, and we'll substitute it in 1. So Vs, and for now we can write this. It's I didn't write this in terms of D here. You can do that. So I'll just write it here now. T on is D times Ts plus Vs into 1 minus D times Ts, and Vc1 I'll substitute it later, which is again 1 minus D into Ts equal to 0. So now we can substitute it. So we have Vs D Ts plus, and this becomes plus now because the minus minus gets cut. So we have this, and if you can see here, the switching time Ts is common with all of them, so you can just make it 0 by Ts, and yeah, that goes away. So now we are left with this. So yeah, now that we have this here, we just have to make just the last few shifts, and we'll have the final equation. So let's shift this Vs to the other side. So let's keep Vc2 into this here itself divided by D, and let's shift this here. Take Vs common. So we can take minus Vs common. So we'll have D plus 1 minus D. And we have to be careful about the signs here. So we took minus Vs out. So now we're safe because we took the minus out. So it's just D plus 1 minus D. So the D is going to get cut. And you're just going to have Vc2 into 1 minus D by D is equal to minus Vs, and that's just multiplied by 1. So as it is. So now if we just write Vc2 is equal to, shifting this to the other side, minus D into Vs by this thing comes down D. And as I said, Vc2 is basically the voltage across the output. So you can just write Vc2 equal to V0, and yeah, that is your duty cycle equation, or the transfer function of the output and the input. So you can see here the formula is same as your buck boost converter, because the Cuk converter, as I said, is a kind of buck boost converter. So the formula remains the same, and if you got this, that means yeah, we can confirm that these equations what we wrote here were correct. So yeah, the first derivation is done here. So now we can move on to the second one, which is the inductor current ripple. And we do need this equation, because if you want to choose your L1 and L2 for a particular switching frequency, supply voltage, and all of that, you need the equation, right? So yeah, we're going to be deriving that. So for this, we'll be needing the fundamental equation again. So we know that the voltage across an inductor is basically L, di by dt. That's the standard equation, L di by dt. So now let's rearrange this. So the voltage across inductor is L into, basically this is delta IL, right? The change in the current. So you can call this D, you can call it delta IL divided by dt, which is delta T, is changing this. And what we want to know is delta L, right? So just shift this to the other side. So we have BL by L into delta T. And let's keep our analysis towards the on state, right? So during the on state, delta L will be VL on divided by L into delta T. And we do know here, if I just go back in the on state, if you see here, this graph, the on time is basically duty cycle times TS, right? So let's just rewrite that. So this is equal to VL on into dTs, the switching time, divided by L. So now we have the generalized equation for the inductor current ripple. So let's apply it to the first inductor. So that is going to be this. So now we can just substitute this again from the same here. So it is basically Vs. So we have Vs into dTs by L1, and you can take the TS down, because rather than the switching time we generally talk about the switching frequency, because let's say 50, 100 kilohertz. So Fs is just the inverse of this, so it's going to be dVs by Fs into L1. So that is the final equation. So yeah, we have derived that. This is a pretty small one. So yeah, we have this. Now for the second inductor, let's go back and reuse this equation. So we have delta IL2 . So now that we have this, let's go back and check what the equation was, and it is minus Vc1 minus Vc2. So let's write that to dTs, or what we could do is just write this separately, VL2 on. So let's just do that. Yeah, I'll move this on top. So okay, VL2 on is this. Let's rewrite that. VC2 is basically V0, as I said, and VC1 we can get this value again from this derivation which we did. That's why deriving the duty cycle first is good, because we get the relation. This was the relation. So VC1 is minus VC2 by D. So if we write this here, minus of minus VC2 by D minus VC2, let's maybe keep that VC2 for now. So we have this. So now that we have this, we can just take the LCM. So now we can go back to this equation and let's write. And before that, we can take Vc2 common. So it's going to be 1 minus D into Vc2 by D. So now substituting this here back in this equation, by D into dTs, the whole thing divided by L2. So the dd is going to get cut here, as we can see. So after that, we're left with 1 minus D times Vc2, and this divided by L2. And same as before, we can take the switching time down. It will be Fs into. So now we can write it as 1 minus D into V0. Now we can substitute that back. because it's basically the same thing, Fs into L2. So we have the duty cycle equation, right? So we can just substitute that here. So V naught is basically minus dVs by 1 minus d, as we did earlier, and whole thing divided by Fs into L2. So now you can see the 1 minus d and 1 minus d can get cut, and we are left. You can see there's a negative sign here, but whenever we talk about the inductor current ripple, it's basically triangular, right? The ripple. So we just take the magnitude. So the sign does not matter here. If you had taken the other direction of the inductor, you would have got positive, but I assumed it from left to right, so I got negative. But you can ignore this sign here basically, since it's only magnitude. So you can write here dVs by Fs into L2. So you can see it's similar to this equation. So yeah, that's the delta IL2. And yeah, now that we derived the inductor current ripple equations, we just have one thing left. We have to do the capacitor voltage ripple, and similarly, because we need to choose the capacitor values, right, depending on your parameters. So we need those equations, and since there are two capacitors, same as before, we need to have two equations. So I'll just add another page. Yeah, we can derive the capacitor voltage ripple equations. So for that, we need to go back to the basic equations. We know that the current through a capacitor is basically this. So we know this, and if we just rearrange it, let's say IC is C times, let's change this to delta VC divided by delta T, and we are interested in the voltage ripple, so rearranging it. So basically 1 by C into IC into delta T, right? So IC by C into delta T, correct. So we have this. So now we need to find we have the generic equation. So now we need to find the current through the capacitor, right? So let's go back to the circuit here, the equivalent circuit, and same as before, we need to look at both states. So you can see here for C1, let's do with C1 first. You can see here that the current through this C1 is basically the IL2 itself, right? Because this is one loop, they are in series. So IC1 is equal to IL2, and assuming that it's leaving this plate, and I assume this direction. So yeah, keep your signs the same so that you don't get any errors. And in the off state here, you can see that it's basically IC1, since it's in the opposite direction, which here I assume this way, and now it's entering this plate. So we can say that it's basically minus IL1. So we have these two equations here now. So let's go back here. So if you just look at the waveform, then it's going to be a square wave, which is going to go between in the on and off state. So let's say this is the waveform. So this is your on time, T on, and this is your off time, T off, or you can write it as DTS as before, same, and 1 minus DTS. So we have this, and we wrote the equations, right? This is in the off state and this is in the on state. So in the on state, it was IL2, and in the off state, it was minus IL1. So you can see it's a square waveform, and to write the capacitor voltage ripple, we can use another equation. We know that Q is equal to CV. That's another standard equation. So if we want to write for the change in charge, since we're looking at only one part of the cycle here, this one, the on one. So C, that remains constant into delta VC. So let's basically delta VC will be 1 by C into delta Q. And how we find delta Q is by finding the area under this curve, which I just shaded, because we know that I is equal to Q by T. So Q is going to be I into T. And since we have the capacitor current versus time graph here, the area under this part should give us the charge. So now looking at the on state, you can see that it's basically like a rectangle. So the area is going to be the area of this rectangle. So that is basically our length into breadth. So if we see our length here, or our base is basically our on time, right? So that is our base into height or length into breadth, whatever you want. So our base is basically dts, and our height here is basically IL2. So yeah, we have that. And now another thing which we see, go back to the diagram and see, IL2 has to supply this capacitor and also this output current, right? It splits. So if we know the KCL here. So let's go back, and IL2 is basically your steady state load current plus this the capacitor current, right? And in the steady state you would only have this, since this is your load current, whereas this is the ripple component, the AC component. So in the steady state we also have, similar to the inductor, we have in the inductor we have the what is that, the volt second balance. In the capacitor we have the ampere second balance, which states that the average current through a capacitor in one charging cycle is zero, similar to earlier. So we cannot have any current in steady state through the capacitor for, of course, ideal case. So looking at that, in the steady state, this would get nullified. So we have IL2 is basically I naught. So we can just substitute that here, dTs into I naught. So now that we have this, let's go back and substitute it into this delta VC equation. So the delta VC1 is equal to IC1 divided by C1 into this. And we know that delta T is dTs, same as before in the on state, and IC. So we could use this equation or this, it would result in the same thing. So just substituting this here, I naught by C1. So similarly, let's take this down. So di naught by Fs into C1. So delta Vc1, and yeah, that is the final equation for your capacitor voltage ripple for the first coupling capacitor, as they call it. So if you wanted to go this way, if you're thinking why I derived this, the charge one, you could again substitute it here, delta Vc equal to this same IC, which is basically your output current, divided by C1 into, and yeah, that is basically the older one, sorry. So this is substituting in this equation, your delta Vc would become 1 by C1 into this dTs into I naught. So as you can see, yeah, it's going to result in the same thing here. So if you go the waveform way, then yeah, you get the same thing. So now moving on to the second one, let's go back to the circuit. We need to look at the second capacitor now. So yeah, let's write the equation. This was for the earlier one. So yeah, now let's look at the current through the second capacitor in the on state is basically, yeah, since the KCL, again, the KCL is always there. So this is your IL2. So your IC2 is basically IL2 minus I naught, and in the off state IC2 is also IL2 minus I naught. So that remains same, since now that this equation wise also we can prove that uh, this has continuous output current. So going back to this place, let's now draw the waveform for this, and this is going to be slightly different than how we derived this. We do have to draw the waveform again though. So yeah, we have this, and if we just look at IL2, then we know that IL2 is, as I wrote here, the same thing. So it's going to be a triangular output. Here it was square. This is going to be a triangle one. So yeah, it's going to look like this, and this is basically your steady state load current, same as this equation, and the ripple, as I said, the ripple component. So this is your total ripple from peak to peak ripple as we call it. This is your delta IL, and in this case we are drawing the graph for IL2, right? So this is delta IL2 total from this peak to this peak, and if we just look at this top peak, it is basically delta IL2 by 2. Maybe that's a little small, make it big. So this is your delta IL2 divided by 2, and yeah, same here, another delta IL2 by 2. So we need to find the area under this curve now in order to, again, similar, same as this equation applies. So we'll use this equation. So delta Vc2 is equal to 1 by C2 into delta Q again. So here in this case, your delta Q is going to be the area under this, and now it is a triangle, so it is basically half base into height. So our this part of it, and yeah, we have this small part. So this is going to be independent of the duty. Here we wrote dts and dt, but this thing is independent. So this is, we can just assume that since one is d and one is 1 minus d, it always halves. So you can take this as half of the switching time. Yeah, this is half of the switching time. So this is your base, and your height is basically delta IL2 by 2. So just substituting that, Ts by 2 into delta IL2 by 2. So you can see here that the IL2 basically, right, the average is going to be this load current, but it does have this ripple. So, and the peak ripple is this. So IL2 is basically I naught, and yeah, I wrote this equation here again, won't write it again. So yeah, let's just simplify this. 2 into 2 into this gives us 8. So 1 by 8 into Ts into delta IL2. So now we can go back and substitute it here. So delta Vc2 is basically your 1 by C2 into, we have this, and yeah, same as before, let's bring this down. So 8 Fs, bringing this down into C2. So finally, yeah, this is your final equation, and you can substitute this delta IL2, which we substituted here, which we found here. You can substitute that back into this, and yeah, you'll get everything in terms of the supply voltage if you want to do that. But yeah, this is good enough to find both of them. So yeah, now we have all the 5 equations needed. We have the duty cycle equation, we have the 2 inductor current ripple equations, and finally we have the 2 capacitor voltage ripple equations. So these are the main 5 equations required, and yeah, you of course later you need to, if you're actually going to implement this converter in hardware, you would have to consider the ESR of the capacitor, the resistance, since they are not ideal, and you have to take into account the maximum saturation current of this inductor, because if you see at any point the current through an inductor is going to be the same, the steady state source or output. So this, in this case, this on the source, this on the output. So either the source or output, or any case the steady state output plus your ripple component. So the peak of that ripple, as I showed here, that is going to be the peak value. So your inductor has to be able to withstand that. So you need to consider this. And of course, yeah, your switches, again, it's not going to be ideal. It has the on state resistance, the diode has a drop. So all of these things are what you would have to consider if you are going to implement this. And yeah, you can check out some app notes for that. I'm sure TI and all of them, they have excellent app notes on this. So, but assuming it's an ideal device, we have all the basic equations here ready. And yeah, that was the whole point of this video, because if you see all the textbooks, they do give all the final equations, same as we did, but they don't do it step by step. So somebody has to do it, right? So yeah, I just took up that. And yeah, I hope you like this new kind of video which I did. And there are two more DC-DC converters. We have the Zeta converter, and another is the SEPIC, the single-ended primary inductor current converter. Those two are also fourth order systems, and deriving those equations as I did here is very similar. You use the volt second balance, you use the ampere second balance, you draw the circuit in the on and off state, and the duty cycle equation, you can derive that. For the zeta, it's basically dVs by 1 minus d. It's a non-inverting step up step down converter. This is inverting, and the SEPIC, same as zeta, non-inverting. So the formula remains same. This part of it remains same for all of them. Just the sign is absent in both of them, since they are same polarity converters. And yeah, you can use the same inductor, and yeah, you draw the waveform for the voltage, and you should be good for deriving it for any of these converters. So I just took up this converter, and using this we can, derive it for the others too. So yeah, I hope you found this video useful. Thank you.